Our familiar three-dimensional world might be just a thin slice of existence. There could be entire realms of reality, entire universes, existing in dimensions hidden from our senses. This is not science fiction, but a serious frontier of modern physics. We are about to embark on an incredible journey through 30 of the most mind-bending theories about these hidden dimensions. You will discover how the universe might truly be constructed of tiny vibrating strings, how our entire cosmos could be a hologram, and why parallel worlds may not be just a fantasy. We will uncover why gravity is so weak, what dark matter might really be, and if the Big Bang was just a collision between cosmic membranes. By the end, you will see reality in a completely new and astonishing light. How many layers do you think our universe truly has? The very fabric of reality might be woven from music. At the heart of string theory lies a beautifully simple yet radical idea. The most fundamental components of the universe are not tiny, solid points, but unimaginably small, vibrating loops of energy. Think of them as the strings of a cosmic guitar. Just as a single guitar string can produce many different notes depending on how it vibrates, these fundamental strings vibrate in unique patterns. Each distinct vibration, each different note, corresponds to a different fundamental particle. One note might be an electron, another a quark, and yet another the particle that carries light itself, the photon. This is the elegant symphony that could construct everything we see. But for this cosmic orchestra to play, it needs a stage with more room than our familiar world provides. A guitar string needs the three dimensions of space to vibrate up and down, side to side. But these cosmic strings require more. To produce the incredible variety of particles that make up our universe, the mathematics of string theory demands extra spatial dimensions for them to vibrate within. We are not talking about one or two extra. The most complete versions of the theory propose a universe with 10 or 11 dimensions in total. We, creatures of length, width, and height, are simply unaware of these additional, hidden layers of spatial reality. This grand idea comes in several variations, like different interpretations of a musical masterpiece. There are 5 major versions of superstring theory, each with its own mathematical structure, yet all pointing toward the same goal, a single, unified description of all the forces of nature. They seek to bring together the laws of the very large, governed by gravity, with the laws of the very small, ruled by quantum mechanics. For decades, these were seen as separate symphonies, impossible to combine. String theory offers the hope of a single, universal score, a theory of everything where gravity, electromagnetism, and the nuclear forces all emerge from the harmonious vibrations of these tiny strings. So the next time you hear a beautiful chord, remember, you might be listening to a faint echo of the universe's most fundamental composition. Yet even this cosmic symphony of strings was not the final composition. The 5 different versions of string theory, while brilliant, presented a puzzle. Why should there be 5 separate theories for one universe? The answer emerged as a grander, more profound framework known as M-theory. Think of the 5 string theories not as competing ideas, but as different views of a single, deeper reality, much like seeing a sculpture from 5 distinct angles. M-theory is the sculpture itself, the master theory that unifies them all. To achieve this unification, it demanded one more dimension, expanding the cosmic stage from 10 to 11. In this 11-dimensional reality, the actors are not just strings. M-theory introduces the concept of membranes, or branes for short. These are not tiny loops, but vast, multidimensional objects that could have many more dimensions than a string. A one-dimensional string is like a line. A 2-brane is like an infinitely thin sheet. A 3-brane has the 3 spatial dimensions we are familiar with. And here is the breathtaking part of the proposal. Our entire universe might not be a place within a larger space, but could instead be a 3-brane itself, a vast floating island of reality. This island drifts within an inconceivably larger space called the bulk, a higher dimensional realm that houses other brains, other universes, each with their own physical laws. This idea of a brain universe elegantly explains one of the most perplexing questions: why can't we see or move through these extra dimensions? Imagine a microscopic ant living its entire life on the surface of a giant taut bed sheet. The ant is aware of the two dimensions of the sheet, length and width, but it has no concept of the third dimension, the space above and below the sheet. It is trapped on its two-dimensional plane. We could be like that ant, but living on a three-dimensional brain. The extra dimensions predicted by M-theory are not dimensions we can travel in, because all the matter and forces we are made of, except for one, are glued to the surface of our brain. They are like paint on a canvas, unable to leave it. The only force that can leak off our brain and into the bulk is gravity. This could be the reason gravity feels so weak compared to the other fundamental forces. Its strength is diluted as it spreads out into the higher dimensional bulk, so the space around you is not empty. It is a dynamic, multidimensional arena, and we are just perceiving the three dimensions of our own cosmic island. The shape of these extra dimensions is not a simple, tiny ball or a loop. It is a specific, intricate geometric form known as a Calabi-Yau manifold. Picture an object of impossible complexity, a six-dimensional shape with a landscape of holes, tunnels, and curves all folded in upon itself. This is not a shape you could ever hold in your hand, for it exists in the six spatial dimensions that are, according to string theory, curled up into an unbelievably small size at every single point in our familiar three-dimensional space. Look at the tip of your finger. Within that single point, and at every other point you can see, there exists one of these complex six-dimensional shapes. They are so small, on the order of the Planck length, that they are completely hidden from our most powerful microscopes. The specific geometry of this hidden Calabi-Yau shape is everything. It acts like the body of a musical instrument. A violin and a cello have different shapes, and so they produce different sounds from their vibrating strings. In exactly the same way, the specific holes and twists of a Calabi-Yau manifold determine how the fundamental strings within it can vibrate. One particular geometry might allow for vibrations that produce the electron and the photon, giving us the universe we know. A slightly different Calabi-Yau shape with one more hole or a different curvature would change the vibrational notes of the strings. This would alter the properties of particles and forces, potentially creating a universe with no atoms or no light, or perhaps with entirely different laws of physics. The very existence of matter, the strength of gravity, and the number of particle generations could all be frozen into the topology of this invisible, six-dimensional knot at the heart of reality. Our entire cosmic symphony, with all its particles and forces, is ultimately conducted by the silent, hidden geometry of the Calabi-Yau manifold. This revolutionary idea redefines our place in the cosmos. We may not be living inside a vast universe, but rather on it. This is the brain world scenario, where our entire three-dimensional reality is a membrane, a three-brain, adrift within a higher dimensional expanse called the bulk. Every galaxy, every star, every one of us is attached to this membrane, like images fixed on a movie screen. This simple yet profound shift in perspective solves one of physics' great mysteries, the puzzling weakness of gravity. While the other fundamental forces, like electromagnetism, are powerful and act within our brain, gravity is trillions upon trillions of times weaker. Why? Because gravity is the only force not confined to our brain. It can leak off our membrane and seep out into the higher dimensional bulk. Imagine a drop of ink on a wet page. On the flat page, the ink creates a dark, concentrated spot. But if that page were a sponge, the ink would spread outwards and downwards, becoming diluted throughout the sponge's volume. Our brain is the page and gravity is the ink. Its strength is diluted as it spreads through the unseen dimensions of the bulk, which is why it feels so faint to us living on the membrane surface. This leakage opens the door to staggering possibilities. If our universe is one three-brain, what is to stop others from existing? The bulk could be filled with a multitude of parallel brain universes, each with its own distinct laws of physics, floating just a fraction of a millimeter away in a higher dimensional direction we cannot perceive. These other worlds would be completely invisible and unreachable to us because the light and matter we are made of are stuck on our brain. We would never see their stars or feel their presence except for one thing: gravity. The gravitational pull from a nearby brain could subtly influence our own cosmos, and sometimes these parallel membranes might not just float peacefully. They could drift, ripple, and even collide. A collision between two brains would be a cataclysmic event of unimaginable energy, an explosion that, from our perspective, trapped on the membrane surface, would look like a fiery rebirth of the entire cosmos. What if our own Big Bang was not a singular point of creation, but the echo of a colossal collision between our brain and another? That colossal collision between brains is not just a possibility, but the centerpiece of a complete cosmological model known as the ekpyrotic universe. Its name comes from the ancient Greek word for conflagration or total fire, a fitting title for a theory that reimagines our cosmic origin as a titanic smash-up. This model directly challenges the standard inflationary Big Bang picture. In the standard view, the universe explodes from an infinitely dense, infinitely hot singularity, a point where all known laws of physics break down. It then undergoes a brief period of hyper-fast expansion called inflation, which smooths it out and seeds the formation of galaxies. The ekpyrotic model offers a compelling alternative that avoids that mysterious initial singularity. Instead of a fiery birth from nothing, our universe began when our three-dimensional brain collided with another parallel brain moving through the higher dimensional bulk. The immense kinetic energy of that impact was converted into the searing heat and dense matter that filled our young cosmos. From our perspective, trapped on the surface of our brain, this event would have looked exactly like a Big Bang, a sudden, hot, and expanding universe. This brain collision elegantly addresses several cosmological puzzles. It naturally explains why our universe is so remarkably flat and uniform on large scales. Before the collision, the two brains could have been slowly aligning and stretching over eons in the bulk, becoming incredibly flat and parallel. When they finally met, that inherent flatness was imprinted onto the newborn universe, eliminating the need for a separate inflationary epoch. This leads to the most profound implication of the ekpyrotic model, the idea of a cyclic universe with no true beginning and no final end. After the collision, the brains bounce apart, filled with the radiation and matter created by the impact. Our universe expands and cools just as we observe today, but gravity, acting across the bulk, eventually overcomes the expansion, pulling the brains back together for another collision. This sets off a new Big Bang, and the cycle repeats. In this breathtaking vision, our entire cosmic history, from the first stars to the last black holes, is just one chapter in an endless, rhythmic dance of creation and destruction, where every ending is merely a prelude to a new beginning. This endless cosmic cycle leads us to a question that challenges the very nature of reality itself. Is our universe, with all its rich depth and three-dimensional solidity, truly what it seems? A startling theory suggests it is not. The holographic principle proposes that our three-dimensional universe is a magnificent illusion, a holographic projection of information encoded on a distant, two-dimensional surface. We may be living inside a cosmic hologram. This radical idea did not emerge from pure speculation, but from the deep study of the most enigmatic objects in existence, black holes. When physicists studied the thermodynamics of black holes, they made a baffling discovery. The maximum amount of information, the total number of bits needed to describe everything that could possibly fall into a black hole, is not proportional to the volume of its interior, as you might expect. Instead, it is proportional to the surface area of its event horizon. It is as if the entire three-dimensional space within a black hole is described by a vast mosaic of information painted onto its two-dimensional boundary. This was a profound clue about the nature of information and space itself. The holographic principle takes this black hole insight and applies it to the entire cosmos. It suggests that our universe operates on the same fundamental rule. The stars, the planets, your own thoughts and experiences, all the information that makes up our three-dimensional reality, could be stored on a giant spherical shell at the absolute boundary of the observable universe. We are not looking at a screen, we are inside the projection that comes from it. Think of a standard hologram like the kind you might see on a credit card. A flat, two-dimensional surface, when illuminated with the right light, creates a stunning three-dimensional image that appears to have depth. The holographic principle argues our universe is a far more sophisticated version of this. The information for every event, every particle, is stored in tiny, plank-sized cells on this cosmic boundary, and what we perceive as reality is the projected image. This rewrites our understanding of space and time. The smooth, continuous space we move through may be an emergent property, a kind of collective effect that arises from the complex interactions of this underlying information network, much like the smoothness of a television picture emerges from the interactions of countless individual pixels. If this is true, then the solidity of the world around you, the very feeling of depth and distance, is a magnificent and convincing illusion. We are all living phantoms in a grand holographic theater. While string theory weaves its symphony of hidden dimensions, a powerful rival offers a completely different vision of reality's foundation. Loop quantum gravity takes the stage, proposing that space and time themselves are not smooth and continuous, but are woven from a fabric of finite, indivisible loops. This theory does not require extra dimensions. Instead, it fundamentally reimagines the very nature of the spacetime we already know. Picture the fabric of reality not as a smooth sheet, but as an incredibly dense, ever-changing web of a billion tiny, interconnected loops. These loops are the atoms of space, the smallest possible units of area and volume. They form a dynamic structure called a spin network, a cosmic mesh where each connection carries information about quantum geometry. The three-dimensional space you move through is not a void, it is this vibrant, pulsing network. The smoothness we perceive is an average, a large-scale illusion created by the unimaginably fine grain of this quantum weave. Much like a piece of cloth appears smooth from a distance, even though it is made of countless individual threads. This radical redefinition of space leads to an even more profound prediction about time and our cosmic origins. In Einstein's general relativity, the Big Bang is a singularity, a point of infinite density where the laws of physics cease to have any meaning. But in the world of loop quantum gravity, nothing can be smaller than a single loop of space. There is no such thing as a point of zero volume. So what happens when we rewind the universe back to its moment of greatest compression? The mathematics reveals that gravity becomes repulsive at these extreme densities. Instead of collapsing into a meaningless singularity, the universe rebounds. The Big Bang was not the beginning, but a transition, a great bounce from a previous cosmic phase that contracted down to a tiny but finite size before springing back into the expansion we see today. Our universe, in this view, could be one in an endless cycle of contraction and expansion, with each bounce resetting the cosmic clock and birthing a new era from the ashes of the old. Long before strings or brains entered the picture, a quiet revolution began with a single, elegant idea. In the early 20th century, shortly after Einstein reshaped our understanding of gravity, two physicists dared to dream of a deeper unity. Theodore Kaluza and Oscar Klein proposed that our universe might not have 4 dimensions but 5. They sought to perform a miracle of theoretical physics, to weave Einstein's gravity and Maxwell's light into a single, seamless fabric within this higher dimensional space. In their five-dimensional universe, the equations for these two fundamental forces emerged from a single, beautiful source, the geometry of the fifth dimension itself. But if there is a fifth dimension, where is it? Why don't we see it? Klein provided the brilliant answer. He suggested this extra dimension is not vast and expansive like the three we know. Instead, it is curled up into a circle so incredibly tiny, a loop with a radius 1,000,000 trillion times smaller than an atom, that it remains completely hidden from our view. At every point in the familiar space around you, there exists this minuscule circular dimension. To understand how this works, picture a long, thin garden hose stretching to the horizon. From a great distance, it looks like a simple one-dimensional line. But if you were an ant on that hose, you would discover a second dimension, the circular path around its tube. You could walk its entire length, or you could take a tiny journey around its circumference. Our reality could be like that. We are like creatures too large to perceive the circular path, forever traveling along the hose's length, width, and height, but completely unaware of the tiny, curled-up fifth dimension existing at every location. The magic of this theory lies in what happens when gravity, described by the geometry of this five-dimensional spacetime, vibrates along this unseen circle. Kaluza and Klein showed that a specific type of vibration in the fifth dimension would not appear to us as an extra gravitational force. Instead, it would manifest precisely as an electromagnetic wave. In this stunning revelation, a ripple in the hidden dimension was light itself. The photon, the particle of light and the carrier of the electromagnetic force, was not a separate entity at all, but merely a ghostly echo of gravity dancing in a dimension we cannot access. Though ultimately superseded by more complex theories, Kaluza-Klein theory was the first courageous step into the world of hidden dimensions, planting a seed that would grow into the sprawling forest of modern physics and forever changing our quest to see the full architecture of reality. Hidden within the mathematics of string theory lies a necessary symmetry, a kind of cosmic partnership so profound it could stabilize the very fabric of our reality. This principle is called supersymmetry, and it proposes a stunning duplication of the entire particle universe. For every known particle we have discovered, from the humble electron to the quirky quark, supersymmetry demands the existence of a hidden, super-heavy twin, a superpartner. An electron would have a selectron, a quark would have a squark, and the photon would be paired with the photino. These superpartners or sparticles are not mere copies. They possess a fundamentally different quantum spin, which means if the known particles are the building blocks of matter, many of their superpartners could be the carriers of the forces that bind matter together. This elegant doubling does more than just fill out a family tree. It solves one of the most pressing problems in modern physics, the hierarchy problem. This is the puzzle of why the Higgs boson, the particle that gives all others mass, is so relatively light. In the standard quantum framework, the Higgs mass should be driven to an astronomically high value by its interactions with other particles, like a boat being swamped by endless waves. But if every particle has a superpartner, their contributions to the Higgs mass would perfectly cancel out those destructive waves. Each particle and its sparticle, though vastly different in mass, would have equal but opposite effects, leaving the Higgs stable and light. This delicate cancellation is a mathematical miracle, but it comes with a haunting consequence. If supersymmetry is a true symmetry of nature, then these sparticles should have the same mass as their ordinary partners. We would have detected them long ago. Since we have not, physicists believe that supersymmetry must be a broken symmetry. The superpartners exist, but they are incredibly heavy, far beyond the reach of our current particle colliders. This very heaviness makes them a perfect candidate for the universe's greatest mystery, dark matter. The lightest sparticle, often thought to be the neutralino, would be stable, electrically neutral, and barely interact with ordinary matter. It would flow right through you and the entire Earth as if they were not even there. Billions of these invisible particles could be passing through your body at this very moment, their collective gravity silently holding galaxies together. Supersymmetry is not just an optional idea. For string theory to be consistent, to avoid mathematical contradictions like faster-than-light travel or negative probabilities, supersymmetry is an absolute requirement. It is the essential ingredient that allows the cosmic strings to vibrate in harmony. So the search for these shadow particles is a search for the hidden partners that complete our universe and validate the very theories that point to worlds beyond our own. This branching of reality begins not with cosmic collisions, but with the simple flip of a quantum coin. Deep within the strange rules governing the smallest particles lies a theory so vast it redefines existence itself, the many worlds interpretation of quantum mechanics. It proposes that our universe is not the only one. In fact, it is just one page in an infinite, ever-growing book of realities. The core of this idea stems from a fundamental property of quantum particles, their ability to exist in multiple states at once, a condition known as superposition. A single electron can be spinning both up and down simultaneously. Only when we observe it does it seem to choose a single state. The conventional view is that the act of measurement forces the particle to collapse into one possibility. But the many worlds interpretation offers a far more radical explanation. There is no collapse. Instead, at the very moment of that observation, the entire universe splits. In one branch, you see the electron spinning up and the universe continues. In another, completely separate branch, a version of you sees it spinning down. Both outcomes are equally real. They simply happen in different, newly formed universes that have decohered, meaning they can no longer interact with one another. This splitting is not a rare event. It is happening constantly at every quantum decision point for every single particle. Every time an atom decays, every time a photon reflects off a surface, the cosmos divides. The result is a multiverse of staggering proportions where every possible outcome that could ever happen does happen somewhere. In one universe, you are reading this script. In another, you decided to click on a different video entirely. In a third, the very laws of physics allowed for a world where dinosaurs never went extinct. Where do all these infinite universes exist? They are not necessarily stacked in some higher physical dimension we could travel to. Instead, physicists describe them as branching through an abstract, infinite-dimensional realm known as Hilbert space. This is not a place you can point to, but a mathematical landscape that contains all possible states of the entire quantum system we call reality. Our universe is just a single point moving along one path in this inconceivably vast configuration space. The implications are both liberating and deeply unsettling. It means that every choice you have ever made and every choice you did not make has been realized in a parallel world. There is a version of you who pursued a different career, a version who lives on a different continent, and even a version who, through a wildly improbable chain of events, became an astronaut. This is not mere speculation about what could have been. According to this interpretation, these alternate lives are all being lived right now, in real, concrete universes that are just as valid as our own. The you reading this is simply the one experiencing this specific branch of the infinite quantum tree. But where do all these branching worlds get their unique rules? The answer may lie in a cosmic lottery of unimaginable scale, a concept known as the anthropic landscape. The fundamental constants of our universe seem perfectly fine-tuned for life. If the force of gravity was slightly stronger, stars would burn out in a cosmic flash. If the mass of the electron were different, atoms could never form. The odds of this precise combination appearing by chance are astronomically small. The anthropic principle offers a straightforward, if humbling, explanation. We observe a universe suited for life because we are here to observe it. In a cosmos where the constants were random, life could only arise in the rare pockets where the numbers lined up perfectly. String theory provides a breathtaking physical mechanism for this cosmic fine-tuning. Remember the Calabi-Yau manifolds, the tiny, six-dimensional shapes that determine the laws of physics. The theory suggests there is not just one possible shape, but a staggering number, perhaps 10 to the power of 500 different configurations. Each distinct shape corresponds to a different vacuum state, a universe with its own unique set of physical constants and laws. This is the string theory landscape, a vast, abstract terrain of possibilities. Our entire cosmos, with all its galaxies and stars, is just one tiny bubble in this landscape, one specific Calabi-Yau shape that curled into existence. In this picture, the multiverse is not just a collection of quantum branches, but a frothing sea of universes, each with a different random set of physical laws. Most of these universes would be stillborn, dark, and empty, incapable of supporting any complex structure. But in a landscape so incomprehensibly vast, even the most unlikely combination of constants is bound to happen somewhere. We do not live in a special universe designed for life. We simply inhabit one of the fortunate few where the cosmic dice rolled in our favor. The very laws of nature we consider fundamental may be nothing more than a local ordinance, a random draw from an infinite deck of cosmic possibilities. This endless cosmic cycle finds its most complete expression in a vision of time without beginning or end. The cyclic model presents a universe that breathes, with each exhalation a grand expansion and each inhalation a slow contraction. In this framework, our Big Bang was not the singular start of everything, but merely the latest turning point in an infinite series. Each cycle begins with a bang, expands for trillions of years, and then, under the relentless pull of gravity, reverses course into a great collapse culminating in a big crunch. This is not an ultimate end, but a cosmic reset. The universe contracts to an incredibly dense hot state, but crucially, not to a point of infinite density. Then it rebounds, exploding outward in a new Big Bang, birthing the next cycle from the ashes of the old. For this grand cosmic rhythm to be possible, our three-dimensional universe cannot be floating alone. It needs room to move. This is where the hidden dimensions of brain cosmology provide the essential stage. Our universe, as a three-brain, exists within a higher dimensional bulk. This allows it the freedom to oscillate, to approach and retreat from other parallel brains over timescales that dwarf the current age of our cosmos. The collision between our brain and another is the engine of the Big Bang, and their subsequent drifting apart sets the stage for the long expansion phase. Eventually, the subtle gravitational attraction across the bulk overcomes the expansion, drawing the brains together once more for another cataclysmic collision. This process repeats forever, an eternal waltz in a hidden dimensional ballroom. What would the end of a cycle look like from within? As the universe contracts over eons, galaxies would draw closer together, their light blue shifting into an increasingly hot, glowing sky. The cosmic background radiation would heat up, eventually overwhelming all structures. Stars and planets would be vaporized, and all matter would dissolve back into a primordial soup, ready to be forged anew in the next great explosion. This model offers a profound alternative to a single, finite timeline, suggesting that existence itself is eternal, with every ending merely a prelude to a new beginning. The end of time does not have to be a cold, dark emptiness. It could be a transformation so profound that it becomes a new dawn. Roger Penrose's conformal cyclic cosmology presents this stunning vision where the universe experiences not just one life, but an infinite series of lives, each called an eon. In this model, the death of our cosmos is not an end, but a cosmic reset button, erasing all information and distinction to create a clean slate for the next Big Bang. The key to this incredible transition lies in a mathematical concept known as conformal rescaling. Imagine taking the entire universe at its final, vastly expanded state, where only stray photons and black holes remain, and shrinking it down in a very specific way. This rescaling does not change the angles or the fundamental shape of spacetime. It only alters its size and mass scales. As the last supermassive black holes evaporate via Hawking radiation, the universe becomes a nearly featureless sea of low-energy radiation. In this state, with no particles with mass and no way to measure distance or time, the universe loses all sense of scale. The infinite future of one eon becomes mathematically identical to the 0 point of the next. The hot, dense, small beginning of a new Big Bang is, through this conformal transformation, the same as the cold, vast, empty end of the previous one. They are two sides of the same singular point in a higher reality. This suggests a hidden cyclical dimension to cosmic time itself, a loop that exists beyond our linear arrow of time perception. We experience time as a straight line from birth to death, but the cosmos may experience it as a circle or an endless spiral of eons. What evidence could possibly support such a grand claim? Penrose points to mysterious circular patterns in the cosmic microwave background, the leftover heat from our own Big Bang. He proposes these could be imprints, cosmic bruises left by the titanic collisions of supermassive black holes from the eon that came before ours. If true, we are not just looking at the beginning of our universe when we look at that ancient light, but we are seeing the ghostly remains of a cosmos that existed an eternity before our own was even born. What if our reality is not the base level of existence? A growing number of thinkers and scientists are seriously considering the simulation hypothesis, the idea that our universe is not fundamental, but a sophisticated digital construct, a kind of hyper-advanced video game running on a computer in a higher dimensional reality. This is not just a plot from a science fiction movie, but a legitimate philosophical argument pioneered by Nick Bostrom. He presents a compelling trilemma, a three-part logical puzzle. He argues that at least one of the following statements is almost certainly true. First, that virtually all civilizations like ours go extinct before reaching a level of technological maturity. Second, that if they do reach that advanced stage, they have exactly zero interest in running simulations of their own ancestral past. Or third, that we are almost certainly living inside such a simulation. If you believe that some civilization could survive and that they might have even a slight curiosity about creating simulated worlds, then the numbers become staggering. Such a civilization could generate billions of simulations, each containing conscious beings who believe their world is real. The vast majority of all conscious experiences would then happen inside these simulations, making it statistically very likely that your own mind is one of them. The scientific implications are just as profound. If our universe is a simulation, then the laws of physics are not fundamental laws, but merely the programmed rules of the simulation, the underlying code. This could explain certain quirks in quantum mechanics, like the way particles seem to exist in multiple states until observed, which resembles how a computer might render graphics only when needed to save processing power. We might even one day discover glitches in this cosmic matrix, tiny errors or inconsistencies in physical constants that betray the finite resolution of the simulation's rendering engine. The very fabric of our three-dimensional spacetime with its smooth continuity could be an emergent illusion, a high-definition projection from a more complex substrate reality that exists in more dimensions. In that base reality, the beings who created our simulation might not even perceive time or space as we do. Our entire cosmic history, from the Big Bang to this very moment, could be a single, frozen data structure that their computers simply execute. This forces a humbling perspective. Every star, every planet, and every one of us would be part of an unimaginably complex computation, living ghosts in a cosmic machine whose ultimate purpose we may never comprehend. Gravity's profound weakness has always been a ghost in the machine of physics. It is the force that sculpts galaxies and holds planets in orbit, yet at the atomic scale, it is utterly dwarfed by the other fundamental forces. A simple kitchen magnet can lift a paperclip, effortlessly overcoming the gravitational pull of the entire Earth. This puzzling disparity finds an elegant solution within the brain-world scenario. All the particles that make up our bodies, our world, and the light we see are firmly stuck to the surface of our three-dimensional brain. They are like actors on a stage, unable to leave it. But gravity is different. It is not a force that travels on the stage, it is a warp in the stage itself. Since our brain is embedded within a higher dimensional space called the bulk, the warps and ripples of space-time are not confined to our membrane. They can leak out. Imagine you are standing on the surface of a vast, still pond which represents our brain. If you drop a pebble, the ripples spread out across the two-dimensional surface, strong and concentrated. This is like the electromagnetic force, powerful and local. Now imagine that same pebble dropped not onto the surface but into the water. It creates a three-dimensional splash, and the energy dissipates not just across the surface, but into the entire volume of the water. This is gravity in the bulk. Its strength is diluted as it spreads into this extra-dimensional volume, which is why, from our perspective on the brain, it feels so faint. This leakage is not just a theoretical idea. It could leave behind tangible, experimental fingerprints. If gravity can move through the bulk, then the fundamental unit of gravity, the graviton, might occasionally travel in these extra dimensions. In powerful particle accelerators, when particles collide with immense energy, we might be able to create gravitons that promptly vanish off our brain, carrying their energy with them into the bulk. From our point of view, this would look like a mysterious violation of the conservation of energy, a clear sign that something is escaping our dimensional prison. Furthermore, the properties of gravitational waves, the ripples in spacetime itself, could be subtly altered by their journey through the higher dimensional bulk. As they propagate, they might develop extra vibrational modes or exhibit a faint echo, a signature that they have been interacting with a reality beyond our own. The detection of such an anomaly would be our first direct glimpse into the hidden architecture of the cosmos, proof that we are indeed living on a fragile island in a much deeper and more vast dimensional sea. This funnel-shaped dimension solves the hierarchy problem with an elegant twist. In the Randall-Sundrum model, the universe is a five-dimensional arena where a single, warped extra dimension stretches to infinity. We live on one of two three-dimensional brains that act as the boundaries of this five-dimensional space, often called the Planck brain and the TV brain. The space between them is not flat, it is curved profoundly and exponentially. Picture this not as a flat sheet, but as a cosmic funnel or a steep gravitational well. Our brain, the TV brain, resides at the deep, narrow end of this funnel. The other brain exists at the wide, open mouth. The warping of this dimension is so severe that the fundamental scale of physics, the Planck scale, is enormously different at the two ends. At the distant brain, the Planck scale is its natural, incredibly high value. But the warping dilutes this energy all the way down the funnel, so that by the time it reaches our brain, it is reduced to the familiar, low-energy scale of the particles we observe. In this setup, gravity feels weak to us not because it spreads into a large volume, but because it is fundamentally tied to the distant brain. The graviton, the particle of gravity, is concentrated over there at the wide end of the funnel. Its influence has to travel down the steep, warped slope to reach us, and in that journey, its strength is exponentially suppressed. All the other particles of the standard model are trapped on our brain at the bottom of the gravitational well, which is why we interact with them so strongly. We are effectively living in a cosmic low-energy backwater, while the true seat of gravitational power exists in a realm far away across a warped dimension we cannot see. This model offers a compelling alternative to the tiny, curled-up dimensions of string theory, proposing instead that the hidden dimensions could be infinite, yet remain hidden by the sheer steepness of their geometry, a curvature so intense it creates a prison for gravity and defines the very nature of our reality. The solid stage upon which we walk may be the grandest illusion of all. Beneath the smooth curves of spacetime described by Einstein, there could be a frantic, churning sea of quantum information. This is the radical proposal that space and time themselves are not fundamental ingredients of reality, but emergent properties that arise from something far more basic. Think of the surface of a still lake. It appears as a continuous, smooth sheet, a perfect stage for reflections. But we know this is an illusion, an average effect created by trillions upon trillions of individual water molecules jostling against one another. In the same way, the seamless, three-dimensional space and the relentless flow of time we experience might be a collective phenomenon. They could emerge from the interactions of unimaginably tiny, fundamental building blocks that themselves have no concept of location or duration. These building blocks are not particles in space, but quantum bits of information, or qubits. They are the universe's most basic yes or no questions, and their complex web of relationships weaves the fabric of reality itself. This is where the holographic principle returns with profound force. That distant, two-dimensional boundary encoding our three-dimensional world is not just storing information like a hard drive. It is a seething network of entangled qubits. Quantum entanglement is that mysterious connection where particles, or in this case information bits, share a single existence no matter how far apart they are in space. The entanglement links between these bits on the boundary create a dense, interconnected web, and it is this very connectivity that, when viewed from the inside, manifests as the geometry of space. A region of space with strong, complex entanglement looks to us like a smooth, continuous volume. A tear or a reduction in that entanglement would appear as a void or a disruption in the fabric of spacetime itself. In this view, the distance between two stars is not a fundamental measurement. It is a measure of how entangled the underlying quantum information describing those stars has become. The force of gravity itself might not be a fundamental force, but a thermodynamic effect, an emergent push that arises from this system's tendency toward higher entropy, much like the pressure in a steam engine emerges from the collective motion of countless molecules. We are not living in a universe with space and time. We are living inside a cosmic computation, a dynamic network where the very concepts of here, there, then, and now are secondary, born from the silent, ceaseless conversations of information across a boundary we will never see. Our most basic assumptions about space and time could be completely backwards. We perceive a universe with three spatial dimensions and one of time, but what if this structure is not a fundamental stage? What if it is more like a weather pattern, a large-scale order that emerges from cosmic chaos? This is the radical proposition of causal dynamical triangulation, a bold approach to quantum gravity that builds reality from the ground up, piece by piece. Forget smooth, continuous spacetime. This theory suggests the cosmos is fundamentally a collection of tiny, simple geometric shapes. The most basic building block is a four-dimensional triangular prism called a four-simplex. These are the atoms of spacetime. In the theory's simulations, trillions upon trillions of these tiny prisms are connected to one another, following two simple rules. They must connect in a way that preserves a clear cause and effect, ensuring that time always flows forward, and they are assembled randomly. This process is like throwing a colossal bag of microscopic Lego blocks into a box and shaking it, allowing them to snap together in every possible configuration. When physicists run this cosmic lottery on a supercomputer, something astonishing happens. From the initial chaotic soup of disconnected geometric pieces, a recognizable universe begins to crystallize. The simulation does not assume four dimensions from the start. It allows the geometry to form on its own, and in a phase known as the extended phase, the connections between the blocks spontaneously organize. They create a smooth, large-scale structure that clearly exhibits 4 dimensions, 3 of space and 1 of time. It is a universe that has bootstrapped itself into existence from pure geometry. This emergence of dimensionality is the theory's most profound insight. The 4-dimensional world we call home is not a prerequisite for physics. It is a collective result, a phase of matter, much like ice crystals forming from liquid water. The properties we take for granted, the very continuity of space and the relentless arrow of time, are not written into the universe's foundational code. They are habits that space-time falls into when a vast enough number of these simple geometric pieces interact. This means that at the very smallest scales, at the Planck length, the concepts of here and there, of before and after, may lose all meaning. The fabric of reality could be a foaming, seething fractal, a constantly shifting mosaic where dimensionality flickers in and out of existence. Only when we zoom out to our human scale does this quantum storm average out into the calm, 4-dimensional continuum we navigate every day. Our smooth, predictable reality is a magnificent statistical illusion, a consensus forged by an unimaginable number of tiny, causal geometric decisions. The sheer number of parallel realities can be overwhelming, but a physicist named Max Tegmark brought order to the chaos by sorting them into 4 distinct levels. Each level explores a different kind of hidden dimension, not of space but of existence itself. The first level is the most conservative and almost certainly real. It proposes that our observable universe, everything we can possibly see, is just a tiny patch in an infinite, eternal cosmos. Beyond our cosmic horizon, a boundary set by the finite speed of light, space continues forever. In that infinite expanse, the arrangement of matter must eventually repeat. There is another planet Earth out there with another you reading these very words. This is not magic, it is a simple consequence of infinity and a finite number of ways to arrange particles. The hidden dimension here is simply more space, vast beyond comprehension, containing endless variations of our own cosmic neighborhood. Level 2 introduces a more profound separation. Imagine our universe as one bubble in a cosmic bubble bath, forever inflating. This is the concept of eternal inflation, where the fabric of space-time is constantly expanding, and new pocket universes continually bud off, each with its own random set of physical constants. Some bubbles might have stronger nuclear forces, forming only hydrogen. Others might have a weaker gravity, preventing stars from ever igniting. The hidden dimension in Level 2 is the landscape of possible physics, where each bubble universe is a separate experiment with different fundamental rules. We just happen to live in one where the rules allowed for us. Then there is Level 3, a realm we have already visited, the many worlds of quantum mechanics. Here, every quantum decision causes reality to branch, creating a constantly multiplying tree of alternate timelines. The hidden dimension here is not spatial, but a vast, abstract realm of quantum possibility called Hilbert space. Every possible outcome of every quantum event exists in its own equally real universe. The you who became an artist and the you who became a scientist are both out there, living their lives on different branches of the quantum wave function. Finally, Level 4 is the most radical of all. It states that every conceivable mathematical structure exists as a physical reality. If a universe can be described by a consistent set of mathematical equations, then it is out there somewhere. This ensemble includes universes with different numbers of dimensions, universes governed by entirely different laws, and realities so alien we could not even begin to imagine them. Our particular universe, with its 4 dimensions and specific constants, is just one mathematical structure in an infinite library of all possible equations. The hidden dimension of Level 4 is the dimension of pure logic and mathematics itself. Tegmark's hierarchy takes us from more space to different physics to branching time, and finally to the very bedrock of logical existence, revealing a cosmos of literally infinite possibilities. Deep within the heart of a black hole, a fundamental law of the universe shatters. The black hole information paradox presents a terrifying conflict between our two most successful theories, quantum mechanics and general relativity. Quantum mechanics insists that information is never truly lost. If you burn a book, the information contained in its letters is not destroyed. It is merely scrambled into the smoke and ash. In principle, with perfect knowledge, you could reverse the process and reconstruct the book. General relativity, however, describes a black hole as a one-way street to nowhere. Once matter crosses the event horizon, it is lost forever, crushed into the singularity. Stephen Hawking discovered that black holes are not completely black. They slowly evaporate by emitting a faint glow of radiation. This Hawking radiation is thermal, it is random heat. It carries no information about the original star, the planets, or the books that fell in. When the black hole finally evaporates completely, all the detailed information about everything it ever consumed seems to have vanished from our universe. This is the paradox. The smooth, deterministic laws of quantum physics clash violently with the destructive, singular nature of gravity. The very fabric of physics seems to tear at the event horizon. Resolving this crisis demands a radical new understanding of reality, one that points directly toward hidden dimensions. One of the most profound solutions is the holographic principle we explored earlier. It suggests that the information is never actually lost inside the three-dimensional volume of the black hole. Instead, it is perfectly preserved, encoded as a quantum fossil on the two-dimensional surface of the event horizon. When particles fall in, they do not vanish. Their information is smeared like a perfect, non-destructive tattoo onto the boundary of the black hole, and it is slowly released back into the universe in the correlations between particles of Hawking radiation. This solution only works if our three-dimensional reality is a projection from a two-dimensional surface, a concept that inherently requires a higher dimensional framework to make sense. We are not looking at the storage device, we are living inside the data it projects. Another breathtaking proposal is that black holes are not endpoints but gateways. The information is not destroyed because it never reaches a singularity. Instead, the black hole's interior connects to another region of space-time through an Einstein-Rosen bridge, a wormhole. This bridge could lead to a white hole in a distant part of our own universe, or it could erupt into an entirely separate baby universe, a new cosmos with its own laws of physics. In this scenario, the information is not lost, it has simply emigrated, traveling along hidden dimensional corridors to a new reality. Our universe could be studded with such portals, each a black hole in our sky serving as a big bang for another world entirely. The information paradox forces us to confront the illusion of our three-dimensional experience. It suggests that the true theater of reality operates on a boundary we cannot see, in dimensions we cannot access, preserving every event, every thought, and every star in a cosmic ledger written in a language of quantum information far beyond our current comprehension. Two particles separated by the vast emptiness of space can share a single existence. Their fates are linked instantly, a phenomenon Einstein called spooky action at a distance. We call it quantum entanglement, but what if this spooky connection is not a ghostly link at all, but a physical bridge? The ER equals EPR conjecture dares to propose exactly that. It suggests that the strange, instantaneous bond of entanglement, the EPR part, is mathematically equivalent to two particles being connected by a microscopic wormhole, an Einstein-Rosen bridge. This is a staggering unification. It weaves together the two great pillars of modern physics, quantum mechanics and general relativity, into a single, breathtaking tapestry. Think of it this way: you see two separate doorways on opposite sides of a city. They appear completely disconnected, but if you could step into a higher dimension, you would see they are actually the front and back doors of the very same building, connected by a long, winding hallway. The ER equals EPR idea says that entangled particles are like those two doorways. From our three-dimensional perspective, they look separate, but in the full geometry of reality, which includes hidden dimensions, they are joined by a tiny, tunnel-like bridge. This provides a stunningly simple answer to a century-old question. What are the hidden variables that determine the state of a quantum particle? The answer may be that there are no hidden variables in the traditional sense. The hidden thing is the geometry itself, a microscopic wormhole threading through the higher dimensional bulk, physically tying the particles together. Their seemingly random, coordinated behavior is not random at all. It is the direct result of this invisible, dimensional umbilical cord. This conjecture transforms our view of the cosmic fabric. The universe is not just filled with entangled particles, it is crisscrossed by an unfathomably complex web of these microscopic wormholes, a cosmic subway system operating in dimensions we cannot perceive. Every quantum connection, every spooky action, is a journey through a hidden dimensional shortcut, making the universe far more interconnected and far more strange than we ever dreamed. The number of possible universes predicted by string theory is not just large, it is a number that defies human comprehension. 10 to the power of 500 is a figure so vast that every atom in our observable universe represents only a minuscule fraction of its immensity. This is the string theory landscape, a cosmic terrain of almost limitless possibilities where every possible configuration of the hidden Calabi-Yau dimensions represents a different valley, a different vacuum state with its own unique laws of physics. In one valley, the curled-up dimensions have a specific geometry that allows for 3 generations of quarks and a force of gravity strong enough to form galaxies. This valley is our universe, but right next to it, in a neighboring valley separated by an abstract chasm of energy, the Calabi-Yau shape might have one fewer hole. That tiny topological difference would change the vibrational notes of the strings, perhaps resulting in a universe where electromagnetism is 1 billion times stronger, instantly tearing apart any atom that tried to form. Another valley might produce a cosmos with only 2 spatial dimensions, a flatland where life as we know it could never arise. The landscape is not a physical place you could travel to. It is a mathematical map of potential realities, and our entire cosmos is just one single, randomly selected point on this map. This concept transforms the anthropic principle from a philosophical curiosity into a physical inevitability. With 10 to the 500 different possible sets of physical laws, it is statistically guaranteed that a tiny, tiny fraction of them will be stable and complex enough to allow for stars, planets, and life. We do not live in a special universe fine-tuned for our existence. We simply inhabit one of the rare habitable islands in a near-infinite ocean of silent, dark, or stillborn realities. Our most fundamental constants, from the mass of the electron to the strength of the nuclear forces, may be nothing more than local geography, the random outcome of a cosmic lottery draw that could have turned out any one of 10 to the 500 other ways. This landscape is the ultimate hidden dimensional reality, a vast, unobservable architecture whose contours silently dictate every rule of our existence. The greatest mysteries of our cosmos might be nothing more than mirages. Dark matter and dark energy, the enigmatic forces that seem to dominate the universe, could be profound illusions, shadows cast by the movement of our own reality through a higher dimensional space. This theory suggests we are misreading the cosmic evidence, like a sailor who mistakes the Earth's curvature for a giant wave. The gravitational pull we attribute to vast clouds of invisible dark matter holding galaxies together might not come from any particle at all. Instead, it could be the subtle gravitational tug from another, parallel 3-dimensional brain floating nearby in the bulk, our galaxy and a nearby brain universe could be influencing each other gravitationally across a hidden dimensional gap, creating the appearance of extra, unseen mass within our own cosmos. We feel the pull, but we cannot see the source, so we invent a dark substance to explain it. Similarly, the force we call dark energy, the mysterious driver of the universe's accelerating expansion, might have a simpler, more startling origin. What if our three-dimensional brain is not static, but is itself slowly stretching or evolving within the higher dimensional bulk? This intrinsic evolution of our cosmic membrane could manifest as an overall expansion of the space within it. From our perspective, trapped on the brain, it would look as if empty space itself possessed a repulsive energy, pushing everything apart. We would call this dark energy, but it would really just be the geometry of our reality changing on a scale we cannot directly perceive. The very fabric of our physics is being written by forces we are blind to, forces that operate in the hidden dimensions that cradle our island universe. This transforms our search for dark matter from a hunt for a ghostly particle into a detective story about the architecture of reality itself. The clues are not in the emptiness of space, but in the unseen dimensions that give our universe its form and its fate. The ultimate goal of this entire journey is a single, elegant equation, a master blueprint for reality known as the theory of everything. For centuries, physicists have chased this unified framework, a set of laws that seamlessly describe the cosmos from the smallest quark to the largest galaxy cluster. We have two incredibly successful but utterly incompatible rulebooks. Quantum mechanics governs the bizarre, probabilistic world of the atom with breathtaking precision. General relativity describes the grand, curved stage of spacetime and the force of gravity with equal brilliance. Yet when these two rulebooks are forced to meet at the center of a black hole or the moment of the Big Bang, the mathematics shatters into nonsense. The equations of quantum physics cannot handle the extreme warping of spacetime, and Einstein's gravity remains stubbornly blind to the quantum weirdness of the very small. This fundamental conflict is the greatest unsolved problem in physics. The quest for a theory of everything is the search for a deeper language, a new set of principles from which both quantum mechanics and general relativity naturally emerge as different aspects of a single, coherent truth. Hidden dimensions are not just a curious side effect of this search, they are its most crucial ingredient. They provide the necessary mathematical room, the extra variables on the cosmic chalkboard, to finally bring gravity into the quantum fold. Think of it like trying to understand a complex three-dimensional object by looking only at its two-dimensional shadow. You might see disconnected shapes and confusing overlaps. But if you could only step into the third dimension, the entire structure would snap into focus, and all the shadow's strange features would suddenly make perfect sense. In the same way, our current theories are like those flat, confusing shadows. The hidden dimensions are the higher perspective that reveals the true, unified object. In the framework of string theory, for instance, the different vibrational patterns of strings within these extra dimensions do not just create particles of matter, they also create the force carriers, including the graviton, the hypothetical particle of gravity. For the first time, gravity is not a foreign concept bolted onto the quantum world. It is woven from the same fundamental fabric as everything else. The dream is that one single type of object, a vibrating string, and one single set of rules, its vibrations in a higher dimensional space, can account for every particle and every force in existence. This would be the ultimate revelation of the cosmos's hidden architecture, a final unification showing that the universe, in all its dizzying complexity, is born from a foundation of stunning simplicity. Finding this blueprint would be humanity's greatest intellectual achievement, finally allowing us to read the hidden lines of code that generate the reality we experience. Deep beneath the border of Switzerland and France, the world's largest machine is hunting for echoes from other dimensions. The Large Hadron Collider, a 27-kilometer ring of supercooled magnets and detectors, smashes protons together at nearly the speed of light. These collisions recreate the conditions of the universe a fraction of a second after the Big Bang, and physicists scrutinize the debris for any anomaly that cannot be explained by our standard three-dimensional laws. They are searching for the fingerprints of the hidden realms we have been exploring. One of the most dramatic signatures would be the sudden, fleeting creation of a microscopic black hole. In a universe with large extra dimensions, the fundamental scale of gravity could be much lower than we thought. This means that at the incredible energies achieved inside the collider, the collision of two protons could concentrate enough energy in a tiny volume to warp spacetime so severely that it pinches off, forming a black hole smaller than a proton. This is not a monster that would swallow the Earth. According to Hawking's theory, it would evaporate instantly in a burst of radiation and particles, a clear and spectacular signal that we have tapped into the physics of higher dimensions. The detectors would see a fiery jet of particles erupting from a single point, the final shout of a tiny black hole born in our lab. Another telltale sign is more subtle, but just as profound: missing energy. Imagine two particles racing toward a violent collision. We can measure their total energy and momentum with perfect precision before they hit. After the collision, we meticulously add up the energy and momentum of all the new particles that fly out. In our familiar three-dimensional world, the books should balance perfectly. But if our universe is a brain and gravity can leak into the bulk, something strange can happen. In some collisions, the energy might not just transform into new particles we can see. It could create a graviton, the particle of gravity, which promptly escapes off our brain and into the higher dimensional bulk. From our perspective, a significant amount of energy would simply vanish. The detectors would register an imbalance, a moment where energy conservation seems to break, pointing to something invisible carrying it away into a dimension we cannot access. Every time the giant detectors record a collision, they are taking a snapshot of reality at its most fundamental. Scientists sift through billions of these events, looking for that one in a trillion anomaly, the microscopic black hole or the inexplicably missing energy that would shatter our three-dimensional worldview and prove we are living in a far vaster, more layered cosmos. The silent ripples in space-time are now a new language for the cosmos. Gravitational wave astronomy has given us ears to hear the universe, and with this new sense, we can listen for the whispers of hidden dimensions. When two black holes spiral into a final, violent merger, they shake the very fabric of reality, sending out waves that travel for billions of years before reaching our detectors. These waves are the pristine messengers of gravity, and their detailed structure could carry subtle scars from a journey through the higher dimensional bulk. If our universe is a brain floating in a greater reality, then gravitational waves would not be confined to our membrane. As they propagate, a tiny portion of their energy could leak into the bulk like sound escaping a thin-walled room. From our perspective, this leakage would cause the waves to arrive at our detectors slightly distorted or weakened compared to predictions. It would be as if we heard a clear, powerful note from a guitar, but the sound was fainter and slightly muffled because some of its vibrations had escaped into another room we cannot enter. Scientists are now meticulously comparing the observed gravitational wave signals from events like black hole mergers with sophisticated computer models. Any persistent, unexplained discrepancy in the signal's shape or strength could be the first direct evidence that these ripples are not just traveling through our three-dimensional space, but are interacting with a larger, hidden architecture. Even more profound are the echoes from the dawn of time. The cosmic microwave background, the ancient afterglow of the Big Bang, is a frozen snapshot of the infant universe. Theorists suggest that if our cosmos underwent a dramatic, higher-dimensional event in its first moments, like a brain collision, the gravitational waves generated would have been imprinted as a unique, swirling pattern in this primordial light. Our most powerful telescopes are now hunting for this specific fingerprint, a faint B-mode polarization signal that cannot be explained by standard physics. Finding it would be like discovering a fossilized ripple from a splash that occurred in a higher dimensional sea, a permanent record of a time when the full, multidimensional nature of reality was violently apparent. Every new chirp from a colliding black hole and every new map of the ancient sky is not just data. It is a potential message, a clue written in the language of gravity about the true, layered nature of our cosmic home. Gravity feels like the dominant force of the cosmos, yet on the smallest scales it is almost laughably feeble. A tiny magnet can lift a paperclip, effortlessly defeating the gravitational pull of our entire planet. This bizarre mismatch is known as the hierarchy problem, and it is one of the most glaring clues that our understanding of reality is incomplete. The strength of gravity is a trillion times weaker than the electromagnetic force that holds atoms together. Why is there such an immense gap between the power that shapes galaxies and the forces that build atoms? The answer might be that gravity is not weak at all, but we are only feeling a faint shadow of its true strength. In a universe with large extra dimensions, gravity is the only fundamental force not confined to our three-dimensional brain. While particles of light and matter are stuck on our membrane, the graviton, the carrier of gravity, can leak off our brain and spread out into the higher dimensional bulk. Imagine you are in a room with a single, buzzing light bulb. The light and heat are intense right where you are standing. Now, imagine that same light bulb is suddenly placed in the center of a massive, dark warehouse. From your small room, the light and heat would seem incredibly faint, diluted by the vast volume of the larger space. Our three-dimensional brain is that small, brightly lit room, and the bulk is the dark warehouse. Gravity's force is not concentrated here with us. It is seeping out into the unseen dimensions, which is why it feels so weak from our perspective. This elegant idea turns the hierarchy problem on its head. The puzzle is not why gravity is weak, but why the other forces are so powerful, confined as they are to our thin slice of reality. The immense energy scales required to unify gravity with the other forces might not be far away in some abstract sense, but could be just a millimeter from us in a direction we cannot point to, hidden within the folded architecture of the cosmos. Empty space is not truly empty. According to quantum physics, the vacuum of space is a seething, bubbling foam where virtual particles constantly flicker in and out of existence. This quantum activity should endow every cubic centimeter of empty space with a tremendous intrinsic energy, a force pushing everything apart. This is the cosmological constant, and its calculated value is one of the most spectacular failures in the history of science. The theoretical prediction for the energy density of the vacuum is a number that is 1 followed by 120 zeros too large. It is off by a factor of 10 to the 120th power, a discrepancy so immense it is the largest gap between theory and observation in all of physics. If the math were correct, this incredible repulsive force would have ripped our universe apart in its first instant, preventing even the simplest atoms from ever forming. Yet when we look at the cosmos, we see a universe expanding at a relatively gentle pace, with galaxies calmly drifting apart. So why is the measured energy of nothingness so much smaller than it should be? This is the cosmological constant problem, and it points toward a reality where our universe is not unique, but incredibly rare. The string theory landscape, with its 10 to the 500 possible vacuum states, offers a profound escape from this puzzle. In that near-infinite array of possible universes, the value of the cosmological constant is not a fixed number. It is set randomly by the specific way the extra dimensions are curled up. The vast, overwhelming majority of these universes would have a cosmological constant as large as the theory predicts, making them sterile, explosive voids where structure is impossible. But in a landscape of infinite possibilities, there will be a tiny, tiny fraction of universes where, by pure chance, the numbers line up just right. In these rare islands of stability, the cosmological constant is small, perhaps even zero. We do not live in a universe fine-tuned by design. We exist in one of the infinitesimally few cosmic lottery tickets where the vacuum energy was accidentally small enough for gravity to pull matter together into galaxies, stars, planets, and us. The cosmological constant is not a problem to be solved by a single equation, but a selection effect. We are here to measure it precisely because in our particular cosmic bubble, the roll of the dice allowed for our existence. Time is the one dimension we feel flowing through our lives, a relentless river carrying us from past to future. But what if this river is an illusion? Physics treats time as a dimension, a coordinate in the four-dimensional block of space-time, yet it feels fundamentally different from the three dimensions of space. We can move freely in space, but we are prisoners to time's arrow, always swept forward. This strange asymmetry has led some physicists to propose a radical idea that time itself may not be a fundamental ingredient of reality. Perhaps it emerges from something more basic, a timeless sea of quantum information or relationships. In a universe where space and time are emergent, the flow of time could be a collective effect, a kind of cosmic consensus that arises from the way countless quantum events become entangled with one another. The past is not gone and the future is not unformed. They may both be equally real, fixed parts of a static four-dimensional structure called the block universe. In this view, the entire history of the cosmos, from the Big Bang to the last black hole, exists eternally. Your birth, your life, and everything that will ever happen to you are already written into this vast, frozen sculpture of space-time. The feeling of a moving present moment is just that, a feeling, a subjective experience as your consciousness traces a particular path through this pre-existing landscape. This leads to an even more dizzying possibility. If time is a dimension, why is there only one of it? Some speculative theories in particle physics allow for the mathematics of two-dimensional time. What would that even mean? In a universe with two time dimensions, causality as we know it would break down. There would be no single linear progression from cause to effect. An event could be both before and after another event, depending on which temporal path you took. History would not be a straight line, but a branching, complex web where events could influence each other in loops. While our reality clearly operates with a single, clear arrow of time, the mere possibility of multiple time dimensions forces us to question the very nature of cause and effect, and whether the steady tick of the clock is the deepest truth of the cosmos. These theories of hidden dimensions force us to confront the very nature of existence. If our solid, three-dimensional world is just a fragile membrane or a holographic projection, then what are we? Our most fundamental assumptions about reality, consciousness, and our own significance are thrown into question. The idea that we are merely one slice of a vast, multidimensional whole is both humbling and liberating. It suggests that the universe is not just stranger than we imagine, but stranger than we can imagine, with layers of existence forever beyond our direct perception. This leads to a radical philosophical idea known as panpsychism. Panpsychism proposes that consciousness is not a rare product of complex biological brains, but a fundamental property of the universe as basic as space, time, and matter. Just as an electron has charge and mass, it might also possess a tiny, primitive form of experience. In this view, the hidden dimensions are not empty. They could be saturated with this fundamental consciousness, a vast, underlying field of sentience. The complex consciousness you experience would then be a rich, concentrated knot of this fundamental awareness, woven together by the intricate structure of your brain. We are not creating consciousness from nothing. We are tuning into a signal that has existed since the beginning, a whisper of awareness present in the very fabric of space-time and its hidden folds. Perhaps these extra dimensions are the very medium in which consciousness resides, spilling over from a realm we cannot access into our own. This connects to an even more ancient question. Where do abstract concepts like mathematics and logic truly exist? We discover mathematical truths, we do not invent them. The number pi exists as a perfect relationship, regardless of whether anyone is there to calculate it. So where is its home? The level 4 multiverse suggests that every consistent mathematical structure is a real, physical universe. But what about the structures themselves? Could the hidden dimensions be the native realm of these perfect, eternal forms? Plato envisioned a world of perfect ideals, a dimension of pure forms that our flawed world merely shadows. Our physical universe, with its 3 dimensions of space and 1 of time, might be just one possible expression of a deeper, more abstract reality that exists in a space of pure information and logic. Your own sense of self, your thoughts and feelings might not be confined to the wetware of your brain. They could be phenomena that straddle realities, with roots extending into these hidden dimensional landscapes. You are not just a ghost in the machine, you might be a ghost of the machine itself, an expression of a cosmos that is, at its heart, both conscious and mathematical, both real and illusory. This final theory does not offer easy answers, but it reframes our entire journey. The search for hidden dimensions is not just a quest for new physics. It is the deepest possible inquiry into why there is something rather than nothing, and what role we play in this magnificent, multi-layered mystery. We have traveled from the infinitesimal vibrations of cosmic strings to the vast, silent architecture of the holographic universe. We have stood on the precipice of black holes and peered into the endless branching of the quantum multiverse. Each of these 30 theories, from the elegance of supersymmetry to the cyclical rebirth of conformal cosmology, paints a consistent and staggering portrait. Our familiar reality of 3 dimensions appears to be a thin slice, a local and perhaps even accidental expression of a cosmos whose true nature is woven from far more threads than we can see or touch. The universe is not just stranger than we suppose, but stranger than we can suppose. This relentless human drive to look beyond the veil, to ask what lies in the shadows beyond our senses, is our greatest inheritance. It transforms us from mere inhabitants of a world into active participants in a grand cosmic mystery, forever reaching for the next hidden layer. The journey does not end here. It continues with every question we dare to ask. Tell us in the comments which of these hidden dimensions of existence resonated most deeply with you. What mysteries keep you wondering about the fabric of reality? If you are ready for the next adventure into the unknown, make sure to subscribe. The universe has countless more secrets left to reveal.